that we finish 1D kinematics, we have to move to 2D kinematics, and perhaps beyond, maybe even three-dimensional. Good news, it's really not that difficult. Bad news is you will have to learn some new math. Most of your life you've done scalar math. Scalars are the numbers you've been used to since almost kindergarten. Addition, subtraction, multiplication, division with numbers, scalars are really simple things. Scalars are mathematical objects that tell you one thing. They tell you the how much, or another word for that is the magnitude. But the world is a little bit more complicated than that. We typically have to account for two or more dimensions, so we need to come up with a math that can incorporate directions. We'll introduce the idea of vectors. Vectors are mathematical objects that are going to tell you two things. They tell you the how much part, or the magnitude like a scalar does, but the vectors also include a direction. So vectors tell you the magnitude, the how much, and a direction. Here's an example. The scalar 3 and the scalar 4 always add up to the scalar 7. But a vector 3 and a vector 4 can add up to anything with a magnitude between 1 and 7, depending how the directions of the two vectors are oriented. Similarly, the directions of adding the two vectors together can be any angle between 0 and 360 degrees. We typically represent scalars by italicized numbers. So anytime you see italicized number, it's pretty much a scalar. Vectors are represented by a bold-faced symbols or symbols with arrows over them, and graphically by an arrow. The length of the arrow will represent the magnitude. So you measure the length, you know something about how big the vector is. The direction of the arrow obviously is going to be the direction that it points in. Vectors are typically drawn in a 2D plane. That's what we'll be working with. So with respect to the traditional coordinate system, we measure the angle from any axis. I typically measure my vectors with respect to the plus x or minus x axis. Here's two ways to represent a vector. A with an arrow over it, or a bold-faced A, and there's an arrow that represents a vector as well. All of these represent vectors. Scalars are the mathematical numbers that tell you the magnitude or how much. Mass and temperature are scalars. We would never say something has a mass of, say, 50 kilograms north. That just doesn't make any sense. Vectors are mathematical objects that tell you the magnitude, the how much part, and a direction. Velocity and acceleration are vectors that we'll use. If I told you you had a velocity of 50 meters per second east, that would make sense. Because of the many physical characteristics of vectors, displacement, velocity, acceleration, and force, we have to be able to add and subtract vectors apart or together. Vector multiplication is a little bit more complicated. Maybe we'll talk about that later. When you draw a vector, you start at the tail and draw towards the tip. The tip of the vector is where the arrow points. So here's a typical vector pointing up to the right. The tail is right here, and the tip is right there. One of the mathematical characteristics, one of the things that makes vectors so easy and good to use, is you can move them anywhere on the paper. A vector remains the same if it has the same length and points in the same direction. So when you add vectors together, you can move them around until they are in the correct orientation. What is the correct orientation? If I want to add two vectors together, the tip of the first vector must touch the tail of the second vector. So we need to move one vector around until its tail is on the tip of the first vector. Here's an example. There's vector A, there's vector B. In this case, B is already oriented correctly to A. The tail of B is on the tip of A. We'll call the sum of the vectors the resultant, or R. To find R, we start at the tail of the first vector, in this case A, follow the arrow of the tail to B, continue around B till we get to its tip. The arrow from the beginning of the tail of A to the tip of B is R, the resultant vector. There it is. The length of R is the magnitude, and the direction that R points is the direction. Here's another example. In this case, the two vectors will not line up properly. In fact, they are tail to tail. One of the biggest mistakes people make is to just connect the tip to the tip. That's incorrect. That doesn't work right. Instead, you need to move B so its tail is on A's tip. Now they're oriented correctly, and we can follow the arrows to find R. So here's vector A. Here's vector B. Notice that they're not oriented correctly. Oh, I've just moved B over. That's a new B moved over to that point. So now it is oriented correctly. I start on A, followed around to B, and there's my resultant vector. Oh, I can also move A around. If I started with vector A, started with vector B and moved vector A so it was oriented correct, I still get the same resultant vector. It doesn't matter the order that you add them. In this example, I did A plus B first, but if I do B plus A, we get the same resultant. Vector addition, like scalar addition, is called commutative. That means what you are doing geometrically is finding the diagonal of a parallelogram. Just make sure you're finding the correct diagonal and that it points the correct way. It doesn't matter where on the paper the vectors are. You can move them to orient them properly. Here's another example. Here's a vector. I'm going to add to it this vector. Well, what do I get? I move them both around so that they're oriented correctly, tip to tail, and there's my resultant vector. It's easy and kind of fun to add these vectors together graphically. However, to be really accurate, I'd have to give you rulers and protractors, and I know none of us are very good at using those. And it's also probably a little too much work. Fortunately, there's a mathematical way. The mathematical way does involve remembering or maybe relearning some basic trigonometry and the Pythagorean theorem. From the trig point, you'll have to remember SOHCAHTOA. We'll be doing primarily two-dimensional vector math, so we'll use the traditional XY coordinate system. Here are 4 points in an XY plane. You see how these points are going to help define a right triangle. The plus or minus axis and the plus or minus y-axis can be the legs of the triangle, and the coordinates xy will define the vertex opposite the right angle. So here are my 4 vectors pointing to those points out there. Oh, here are the right angles, or the other vectors I can draw in there. Notice I've made right triangles. I always have vectors along the x-axis pointing either plus or minus x, and then other ones pointing in the plus or minus y direction. Remember, they don't have to be along the plus or minus y axis directly. They can be parallel to it as long as they're the same length and point in the same direction. This should show you that any point in the xy plane can be defined by x comma y, or any vector in the xy plane can be represented by an x vector and a y vector. Let's look at a vector in the first quadrant. Here's an example. Let's define the point 3, 4. Here's my coordinate axes again. There's my point 3, 4. There's going to be my x vector, 3, 0. There's going to be my y vector, 0, 4. The length of the side on the x-axis is 3 units long. The length of the side on the y-axis, or parallel to the y-axis, is 4. I can use the Pythagorean theorem to find r, since x and y are perpendicular to each other. There's my hypotenuse. I added in there. I find r squared is equal to 3 squared plus 4 squared. That's 25, or r is going to be 5 units long. If I want to find the angle, I guess I could use the TOA part. TOA means that the tangent of the angle is equal to the opposite side divided by the tangent side. I have to find a way to describe that, so I'm going to use the trigonometry to do this. What do I get? My angle is going to equal the inverse tangent of the opposite over the adjacent. In this case, it was the inverse tangent of 4/3, or 53.1 degrees. You can refer to the vector 3, 4 as 5 units at 53.1 degrees above the positive x-axis. Both representations of this vector have 2 pieces of information. They tell us the same thing, just in different forms. Why is this so important? Any vector in any quadrant can be represented either way. The r at theta shows the direction and the length in a clearer way, but the x and y form makes vector addition much easier. Now, note how I've included which axis I measure the angle from. I need to do this, so I wanted to find my angles between 0 and 90 degrees. I really don't know trig for angles greater than 90 degrees. I only like to work with right triangles. I would prefer and want you to refer to the angles in the same way. I typically measure my angles from the plus or minus x-axis, and I say they're either above or below those axes. If I have an example, let's say the vector minus 3, 4. This would be in the second quadrant. I would refer to it to 5 units at 53.1 degrees above the negative x-axis. How about minus 3, minus 4? That looks like it's going to point into the third quadrant. So I'd refer to this as 5 units at 53.1 degrees below the minus x-axis. And finally, if I had one in the fourth quadrant, 3 minus 4, 5 units at 53.1 degrees below the positive x-axis. This way, you only deal with right triangles, and you only deal with angles between 0 and 90 degrees. Notice that I haven't put any units on the vectors. Even though we measure the length of a vector in meters or centimeters or some length, the units can represent anything that is a vector, like a displacement, or a velocity, or an acceleration, or a force. You always need to include units when representing a vector. When vectors are listed in the XY form as an ordered pair, we say that they are in component form. There is an X component, that would be the X value, and a Y component, that would be the Y value. You've seen how to convert X and Y into R theta. You have to go the other way. If I'm given a vector in the form R at theta, you need to be able to put it in the XY form. This will also involve some trigonometry. I guess I have some vectors and angles already drawn. Here's my coordinate system. Oh, and there's my hypotenuse. I have an angle, and I have my 2 legs. Here's a vector in the first quadrant. Notice how it is the hypotenuse is a right triangle. I need to find the 2 legs of the triangle. One leg is along the x-axis, the other is parallel to the y-axis. The x leg, is the adjacent leg to the angle, and the y leg is the opposite leg to the angle. There's the adjacent and the opposite, and then I have the hypotenuse. To find the adjacent side, I need SOHCAHTOA. Specifically, well, let's see, I have the adjacent and the hypotenuse. That's the ka part. What does that mean? The cosine of my angle is equal to the adjacent over the hypotenuse. If I rearrange that, the hypotenuse times the cosine of my angle will be my adjacent side. To find the opposite side, I have to use the SO part. I know the opposite in the hypotenuse, so I use the SO of SOHCAHTOA. Same thing. Sine of theta is equal to the opposite over the hypotenuse. Rearranging mathematically, my hypotenuse times the sine of my angle, theta, is equal to the opposite. Oh, I guess I've drawn some more vectors in here already. Sorry about that. Let's try an example. Giving you a vector of 24.5 meters per second at 48.3 degrees above the x-axis. This is a vector pointing into the first quadrant. There's my coordinate axes, and there's my vector. I've already drawn the blue x and y legs in there. Oh, it's 24.5 meters per second at 48.3 degrees. Notice in this case, the units represent a velocity. There's my opposite and my adjacent sides. Well, I just do the formula. The cosine of 48.3 is equal to the opposite or the adjacent divided by the hypotenuse. Rearranging 24.5 times the cosine of 48.3, I get 16.3 meters per second. Similarly, I do the opposite side. Sine of 48.3 is opposite over 24.5. Multiplying or rearranging 24.5 times the sine of 48.3, I get 18.3 meters per second. So, the vector 24.5 meters per second at 48.3 degrees above the x-axis can also be represented by the ordered pair in component form as 16.3, 18.3, and then I put the meters per second outside the ordered pair. In this case, both the x vector and the y vector pointed in the positive directions, so both the x and y components are positive. I've already drawn the arrows again, sorry. Here's another example, but in this case the vector is going to point into the second quadrant. Let's say it's a vector of 47.8 meters at 25.6 degrees above the negative x-axis. There's my coordinate system, and there's my hypotenuse. I've already drawn the legs in, the blue legs in. 47.8 meters, 25.6 degrees. I do everything exactly the same way. But here's where the difference comes in. Notice I did the cosine. Cosine of 25.6 is equal to the adjacent over 47.8. Solving for that, I get 43.1 meters. I do the same thing for the sine. In this case, I find it to be 20.7 meters. But here's the difference. Notice that the x vector, the vector representing the x value along the x-axis, points in the negative x direction. That means the x component needs a negative sign in front of it to indicate that direction. And this is what you have to put in. The calculator won't put that minus sign in for you. You have to put it in looking at the drawing that you've drawn. The y vector in this case points up, so it's already positive. So in this vector in component form is minus 43.1, 20.7 meters. Again, note the minus sign in front of the x component. You had to put it in because the original vector pointed into the second quadrant. The rule from the last slide applies to any vector. Make sure you draw the vector correctly, pointing into the proper quadrant. Then you have to add the minus sign when appropriate. In the first quadrant, both x and y are positive. Second quadrant, x is negative, y is positive. Third quadrant, they're both negative. And in the fourth quadrant, I have a positive x and a negative y. Also, I'd like you to be careful about the triangles involved. You may get used to, from your trig class, to associate x with cosine and y with sine. It doesn't always have to be that way. Sometimes you may draw your triangles a little bit differently so that the adjacent side may represent a y value and the opposite side may represent a x value. So it's better to relate the adjacent to the cosine and the opposite to the sine rather than the other way around. Sometimes we are given vectors that are just completely along a particular coordinate axis. In that case, you really don't have to do trig, you just write the vector down. Here's an example. 1.25, 0 meters per second squared. That's a vector representing acceleration that is along the x-axis. So I could just say 1.25 meters per second squared along the x-axis. You could put 0 degrees if you wanted to, but I just like writing the words down. Here's another vector, a vector that is 22 meters per second along the negative y-axis. Well, I can write that as 0, minus 22 meters per second. Finally, we're at the point where we can add vectors together analytically. Analytically means with math, so we finally get to do some math. To add vectors together, you need to put all the vectors in the component form in the terms of x and y. Once you do that, you just add all the x components together, you add all the y components together, and that gives you your resultant. Here's an example. Vector A, 12.6 minus 34.7 meters per second. Vector B, 45.0 meters per second and 67.8 degrees above the negative x-axis. Vector C, is 18.9 meters per second along the y-axis. Vector A is already in the correct form. Don't need to do anything about it. So there's my vector A. B, I got to do some work. It points into the second quadrant, so my x will be negative and my y positive. Doing what you did a few slides ago in finding the adjacent and opposite sides, you should find that the adjacent side is equal to minus 17 because it's pointing left, and the opposite is 41.7 because it's pointing up. So B can be written as minus 17.0, 41.7 meters per second. Make sure you can get the same values I do when you do the math. There's vector B. C is relatively easy. I can just write that easily as 0, 18.9 meters per second. So there's my C vector. Now I add the components together. I just add the x's together, I add the y's together, and I get that resultant vector of minus 4.4, 25.9 meters per second. So my resultant vector is just what I just said. Now you have to untrigonomify that, putting it into the r and theta form. You know how to do this, but let's finish this to make sure. So as I said before, the r is minus 4.4, 25.9 meters per second. Let's draw it out so you can see the triangle. There's my coordinate system, there's my x and y vectors, and there's my hypotenuse. Using the Pythagorean theorem, r squared is going to be 4.4 squared plus 25.9 squared. I get it to be 26.3 meters per second. Finding the angle. Theta is going to equal the opposite over the adjacent, so it's going to be the inverse tangent of 25.9 over 4.4. That's 80.4 degrees. So when I add my vectors together, A plus B plus C is going to either be minus 4.4 comma 25.9 meters per second or 26.3 meters per second at 80.4 degrees above the negative x-axis. That's it. That's it, how to add these vectors together and how to do the trigonometry. It's a little bit complicated, but none of it is overwhelming. You need to know right-angle trigonometry, you need to be able to draw right triangles, and you need to be able to do SOHCAHTOA. I want you to practice these, and then anytime we use vectors, these are the skills you use for the rest of the year.